here's the squeeze theorem. Suppose we have three functions g, f, and h, such that f is enclosed between g and h. If the limit of g as x approaches a is equal to the limit of h as x approaches a, then the value of those limits is also equal to the limit of f of x as x approaches a. This is useful when the limit as x approaches a of f is very difficult to determine. So if we have f of x equals x sine 1 over x, obviously we can't just substitute in, and there's not really a logical way to do this other than by following the squeeze theorem. Here's what this might look like graphically. We have this lower function g and this upper function h, and this middle function f. Maybe we're trying to determine the limit as x approaches 0 of f, but maybe that's really difficult just using algebra. So we squeeze it between these two simpler functions that just look like parabolas, and we evaluate the limits of these at 0. If they're equal, then we know the limit of f is as well. So here's a problem we did in class. What's the limit of x squared sine 1 over x as x approaches 0? So first we have to turn this into an inequality. So what do we know about sine of x? Well, no matter what the value of x is in sine 1 over x, we know it's always going to be between -1 and 1. It follows that this inequality is true too. So we evaluate the limit for the lower and upper bound. This limit, obviously 0, this limit, obviously 0. Most important, now that we have everything that we need to know, we have to say, therefore, according to the squeeze theorem, the limit of this function as x approaches 0 is 0. It doesn't have to be phrased exactly like this, but the AP markers are looking for a specific reference to the theorem. It's always good to have a graphical understanding of this. If we look at the function, we see this rapid oscillation towards 0, and using these two surrounding functions, it's obvious to show that it approaches 0. So here's a good review. Give it a try on your own, and I'll show you the solution. So what we want to do is construct the original function by using an inequality. So in the first step, we build this inequality. Then we multiply by -1. Notice we flip the signs here, which we'll just undo real quick. Now we want to add this 5x squared term. Then to get us to our original function, we just divide by x squared plus 10. Now we find the limits of either of these bounding functions. So if you're doing multiple choice, you can just evaluate these by inspection, the leading coefficient of the numerator over the leading coefficient of the denominator, you get 5. But if you're doing a written, you want to remember to actually show that using limits. So again, don't forget to show, according to the squeeze theorem, this limit equals 5. So again, it's good to have a graphical understanding of this. So when we graph this function, we get this funny wobbly thing towards 0, and we get closer to 5 as we go to infinity. Our two functions, g and h, actually hug it very closely and only get closer as we go to infinity. So in conclusion, when you see a tricky limit like one of these, you start with that inequality, construct the original function using algebra, show that those outer limits are the same, and then state, therefore, according to the squeeze theorem, your inner limit is also the same.